All right, kids. So buckle in. We're going to be here for a while. I hope it's not too long. But yeah, first one back from the holidays, you should all be nice and relaxed. So today we're going to look at the model of the atom and how we got there. So basically, by the end of this, you should be able to describe the current model of the atom and the previous models of the atom. So good luck. Now, we know that the interactions between atoms are due to their structure, and they've known this for a very, very long time. And that it's the physical characteristics that determine where it is in the periodic table. And we'll get more to that later on. All right, Dalton, 1803, okay? Now, these are the dates. We're going to give you a lot of dates here. If you wanted, you could potentially make it a timeline. You don't have to, but, I know how much you love them. So, here we go. So he was an English chemist who proposed that matter was composed of atoms, okay? So small, indivisible units. That's what an atom is. An atom is a small, indivisible unit, except it's not. But that's what they thought it was at the time. So each atom has its own atomic mass, and this was relative to hydrogen. Now, a lot of the time when we measure things, if we don't have exact measurements, we base it on something. So it's a relative measurement. This is one of those. He did it with simple chemical analysis. So the ratios of things used up in reactions, gravimetric analysis, the stuff that you can do in a lab now. If you would really put your mind to it, you can sit here and knock out a theory of an atom similar to Dalton. So basically his model was that small indivisible spheres similar to our simple particle model. Now, just before you start freaking out, you see the time. Don't stress. You don't have to write all of this down. I'll tell you when the important parts stop. It's not now, though. Keep going. Okay, so this is his atomic theory. Basically, everything's composed of elements. All atoms of the same element are identical. Atoms of one kind differ from all of the other different types. They're indestructible and retain their chemical identity in reactions. Get rid of that one. Actually, no, hang on. We'll keep part of it. That there. This bit here, that bit's wrong. And compounds are formed by joining specific whole number ratios. And to be honest, this is, for all intents and purposes, for the use that we have it, this is where his falls down, is the indestructible part. Yeah, we'll get to that in a second. So we've got Crookes. He was a physicist. He wasn't a chemist. And he actually did something slightly different that informs the next guy, but he's pretty rad. So he discovered that rays, so you get a gas, and you pump electricity through it, enough of it, like at a high voltage, boom, light happens. He worked that out because he's awesome. And you use that in fluorescent tubes, energy-saving light bulbs. That's not what he used it for. He used it for this other stuff. So he called these rays cathode rays. They have mass, and we know they have mass because they had these, like, he had the tube that was like this, and he'd have like a thin bit of, we'll call it, I don't know, whatever, it doesn't matter, really thin bit of metal there, and as the rays hit it, they cause it to move, which is pretty cool. So they were able to move thin metal veins, like weather vanes. The weather vane is that chicken you see on the top of your roof and it spins around. Alright, Thomson. Now, he's a man. We dig Thomson. 1909, he found that the cathode rays in Crookes tubes were attracted to a positive electric field. This means they have a negative charge. So if you're thinking, you already know what these are made of, these rays. But hang in there. So they were beams of individual particles. We know they were particles because they had that mass, because they could move the vein. And this means he discovered electrons. So, winner, chicken dinner. That's pretty exciting. It looks like this, okay? So he had a negative field here, positive field, electric field, which means it's electronegative, because they went along and instead of hitting the end here, which is what they were attracted to in the first place, they were and hit on the side. And you do this with like phosphorescent paper, so when the electrical particles hit it, it glows, and you can see that. So he showed that cathode rays were caused by electrons colliding with neutral gas atoms, which is pretty cool. So what you're actually seeing is you don't see the electrons flying across, but you see the gas getting excited as some of them don't make it all the way through. That's exciting. You're in the way. Alright, so cathode rays were the same regardless of the gas tubes. This means they're fundamental. This means they're the same in every single atom, and that's exciting. We found another part of the atom. It's no longer, as Dalton put it, indivisible. We've got indestructible. We've got parts coming off it, and it's fundamental because it's the same every single time. All right, so he's in the way. Okay, so plum pudding model is basically the negative electrons are embedded in a positively charged nucleus. So there we go. We've said that for you. So positively charged solid ball, and the negative electrons are embedded in it. And we see it here. So you get positively charged pudding. That's what they call it. And the electrons are embedded. Now, you punch electricity through it. The electrons fly off. Boom, and you get a positive ion. Okay, so they knew about positive ions already, but this is how they're formed. Cool. Rutherford, the classroom hero. We love him. He's awesome. His work's amazing. So his work says beyond cool, which allows him to be basically a massive tool forever. All right, so we had some technical difficulties. We've moved stuff around. We're back. Rutherford, again, classroom hero. He's awesome. And because his work was so cool, he gets away with being a massive tool forever. And he was an experimental physicist, and he was awesome. So he basically fired beams of alpha particles. Now this means it's a so an alpha particle is a He2 plus nucleus. So what that means is it's a nucleus of helium with all of the electrons stripped away. So he fired beams of these into gold foil. Most went straight through. And he was all like, oh, what's this mean, bro? And what it meant was that, okay, cool. What it meant was that most of the atoms, they aren't solid, bro? They're really, there's lots of space in between. Most of the atom is empty. That's amazing. What that means is that this plum pudding can't be correct, because if it was, they'd all be sitting on top of it and you couldn't squeeze anything through. So the nucleus is really, the positive part's really tiny, and most of it is taken up by about most of it's taken up by he worked it out as the electrons floating through it. So there's always space in between them, which is cool. So they're not actually touching. That's pretty awesome. He called his model the planetary model. We'll get into his work just a bit more. So this is what it looked like. He's got his gold foil, his radioactive source, and just they all fly through. Most go through undeflected, they just go straight through. This means, okay, so here, this is an observation, this is an inference, or his conclusion. So atoms won't see his face. Some were deflected at small angles. Okay, this means that the nucleus is positively charged, like the alpha particle. So as it flies through, it gets close and it veers off. Okay, it does can't say that. Occasionally, one bounces right back. And this means if it bounces directly back, it's hit a solid thing of about the same mass, which means the nucleus is carrying most of the mass. So that's cool. Anyway, Rutherford's rad. This is his atom. So you've got the nucleus in the middle. He didn't know about that yet. Positive nucleus, electrons spinning around. So mass of the electron is 1/2000th that of a proton, and the mass of the proton equals a neutron. Again, don't know about neutrons yet. We'll get to that. Alright, so Bohr's model of the atom. He's our man. Bohr studied that basically when atoms get excited or hit electricity, boom, they let off light. And it's different for each one. So light's produced when they're excited by heat or electricity. And also, there's one other thing that comes with that is when they have energy hit them, they absorb it. And that means when they let the energy go, they let the electron go, they let off light. When energy hits them, they absorb it, so they actually absorb light, which is pretty cool. We'll get to that in class. So Rutherford's model, Rutherford couldn't explain why unique colours were obtained by different elements. He's like, oh bro, I don't know, And it turns out that Bohr was a student of Rutherford. He was much younger, and he was a student of his. But I don't know why I struggle with that one. That made perfect sense. And Bohr proposed that electrons are in orbits, and when they get excited, they jump up. That absorbs lights. But when they are no longer excited, they go boom, and that's what releases the light. Okay? So, basically, he's the one who gave us orbits. Now, as the energy gets excited, it absorbs light, and as it cools down and chills out, it then lets off the light. So this means that we now have orbits. We have a set spaces for our electrons to go. And if they're individual, if they're unique, then we have atoms that have specific orbits to each atom, which is also really rad. Okay, so then along comes Schrodinger. It just messes everyone up. By the way, that's the model we use. We use Bohr's model. We talk about Schrodinger's, but when we get you to draw stuff, we're using Bohr's. Schrodinger's is correct, or more correct, is the way we should talk about this stuff, but Bohr's is the one we use. Okay, so we talk about it in terms of Schrodinger, but we use Bohr's model. Alright, so Schrodinger, he proposed the wave mechanical model of the atom. This is quantum mechanics, and this is so exciting, and you don't have to understand it because no one does, not really. There's like 6 people, it's that many, that understand this perfectly. I'm not one, you're not going to be one, at least in the next 10, 15, 20 years. So don't stress, you might get there if you work hard. Electrons are treated as standing waves. This means that as they go around, their wave fits perfectly, so it just stays in there. Okay, it's stuck at that level. If it was bigger, if the wave was bigger, it would not fit, it would overlap, and it would cancel itself out. So this basically allows Bohr's model to work. But instead of being an orbit, it's a cloud, okay, of probability. Now, this is where quantum mechanics gets weird, because we can't talk about the location of the nucleus of the electron. We can only talk about where it's likely to be. So electrons no longer appear as little dots going around. They appear as clouds where it's somewhere in there, where you've got regions of high probability and regions of extremely low probability. Again, that's for later. So the electron cloud. We're almost finished the point we have to write, and then you can just listen for a little bit. So the electron cloud represents position where it's likely to find one. The higher the density, the higher the probability, basically, that electron may be found in that region. So electrons are located in specific energy levels. There is no exact path around the nucleus. In actual fact, what we know about it is that each electron takes all paths around the nucleus at the same time, which is really crazy. So the model estimates the probability of finding an electron in a certain position. Alright. You know what, we'll call it there, and I'm not going to worry about the rest. Enjoy.